Our aim here is to develop some strategies to handle three-dimensional trigonomic problems, and three-dimensional of course means that we can see it from different views. So we've got a depth, a length, a width if we put it inside a box, inside a prism, or in other words we can see a plan view from above, and we can also see a profile view from the side. So we've got both of those. So it makes it more sophisticated than just two-dimensional stuff that we've been doing so far. We've got an example here. A cube has sides of length 10, so they're all 10. Find the angle between the diagonal AB of the cube and one of the edges at B. So one of the key stages is to predict and clarify. So we might be using Pythagoras, we might be using trig. If this video is about trig, so yes, we're going to use trig. But if you didn't know that, you think, well, right angle triangle, right angle triangle, we might have trig, we might have Pythagoras, or both, and we predict that it's going to be something to do with those. And look, we need to clarify too, what does a question want us to find, which angle. So let's draw in some lines to clarify that. So AB is from the bottom corner here up to the opposite corner on the top, so it goes up and across. So that's with some 3Ds kicking in, right? And one of the edges at B, now all of the edges at B are the same, so I'm going to use C, because see, it's already marked in there, so it's a bit of a hint. And we need to find this angle here. So that's the clarifying what we have to find. So it's that angle there. Alright, and so we need to close this so we get one of these predict things, a triangle, right angle triangle with trig or Pythagoras available to us, and yes, we can close that there. Now think about that, that's the base of the cube, so that's a vertical line, that's a base, and so we've got a right angle there. So we've got the right angle triangle ABC. So let's isolate that and draw it by itself. And we need to find angle theta, the unknown angle. We know that the side lengths are 10, so on the cube BC, for example, would be 10 centimeters. So we can mark that in on this one, BC. None of the other sides involved in this triangle here are 10, but because this one's going to be, AB is going to be longer than 10, AC is going to be longer than 10, so we need to do some extra work before we can use our trig. So we've got to go back to go forwards. Alright, so are there one of these two sides, AB or AC, that we can find so that we can then go back to that triangle there? Let's look at the base of the triangle. So this would be 10. The base of the cube, I should say, not the triangle, the base of the cube, that should be 10, that would be 10, that would be 10. And that means we can work out AC using Pythagoras. So looking at the base of the cube, so that's the bottom of the cube, redrawing that. So drawing diagrams is good to clarify things. If you're not drawing diagrams, you might not be doing this right. So that's AC there. And I shouldn't have put C there, it's better. So that's AC, and we know that we've got 10, 10, and we can put a right angle in there, and with Pythagoras' theorem we can basically find out AC, because AC squared equals 10 squared plus 10 squared. So AC is the square root of, using Pythagoras, 10 squared plus 10 squared. So we did predict that maybe Pythagoras will be involved, and here we are. So that's square root of 200. So if you know surds, you can split that into 100 times 2 with a square root over both 10 root 2, or if you haven't learnt that yet, you can just estimate that with your calculator. So square root of 200, and you get an estimate of it, so 14.14. I think that's meters, is it? Centimeters. It's rather small, isn't it? Okay, so remember that the weakness of the 14.14, it's only an estimate. The actual exact value is 10 root 2, but if you haven't learned how to deal with surds yet, or what they are, you'll need to stick with the 14.14. We can put that on this diagram now, because AC is AC, strangely enough. Alright, so that's 14.14 centimeters as an estimate. Now we can find theta because we have two sides and an angle, and we can use trig. So what have we got? Opposite and an adjacent, so we go tan theta is 14.14 over 10. So to get the angle, we go inverse trig, so inverse tan 14.14 over 10, and we calculate that. We get 54.73 degrees. That answer does seem reasonable, because it's going to be more than 45, because if you look at the size of these sides here, if it was 10 versus 10, that theta would be 45, but it's going out to the side further, so that's going to make the angle increase beyond 45 a bit, and yeah, 54 is a bit bigger than 45. That seems reasonable, so it's good to reflect on your answer when you're problem solving. The second and final example is a more difficult one, and it is three-dimensional. So let's clarify the problem first. From a certain point A, a mountain peak due north has an angle of elevation of 20 degrees. So we've got both bearings along the ground, and we've also got vertical elevation as well above the horizontal. Okay, from another point B, which is 2 kilometers east of A, it's on the same height or level as A. The bearing of the peak is north 40 degrees west. Find the height of the peak above the level of A and B. Okay, a lot to think about there. So we break it down, and that's a direction, north 40 degrees west. So that's, as a bearing, we've basically got, we go to north and then we go west by 40, so that's backwards anti-clockwise by 40 degrees, so that would be 360 take 40, and that's a bearing of 320. Perhaps you might wanted to have clarified that. So there we go. What I'm going to suggest on this one is to look from the profile from the side. Okay, so looking from the side, or a profile view, and then I'm going to look at from above, which is a plan view. This is one strategy when you look at each side and do a diagram for each, not each side but each perspective, and you draw a diagram accordingly. If we go back to the first sentence here, if something is due north, okay, so from A, so we need to put in the point A, that's where we're starting, and due north as a bearing would be going like that. So that's from above, and we got some peak here. I'm going to call the peak P. Need to label points. Okay, we don't know how long that is. Next bit of information. From the side view, that has an angle of elevation of 20. So there's A along the side, and basically we've got a horizontal, and to get up to P we've got to climb an angle of elevation of 20 degrees. So we might have something like that. P would be up there. So that's 20 degrees. So we've got two diagrams going now. from another point B, which is 2 k's east of A. Now east, we're going back to this diagram, so it's east of A. B's there somewhere. It's, in fact, we are given that it is 2 kilometers, so we know that. We're also told that it's on the same level as A, so B would be over here. We're told the bearing of the peak, okay, it says here the bearing of the peak is north 40 degrees west, so B back to the peak is north 40 degrees west, so that's that first step there, that's the bearing we've got to plot. So from B it's basically on a bearing of 320 degrees or north 40 degrees west, so it's like that. Now that would create obviously a 40 degree angle there because it's north 40 degrees west, so that would make this angle here 50. So we've got an angle, this is a right angle triangle, we're in business. Question says we have to find the height of the peak above A and B's level, so that's the vertical side profile diagram, so we have to find H. Okay, so trouble with this top diagram is we only have one bit of information. We have 20 degrees. We need a second piece of information. Can we get it from the diagram below? And that's what we need to look at. One thing we can do is find PA, which will end up being the same PA is there. Sorry, not there, here. Because, apologies for that, I wrote it in the wrong spot. Because that, if you think about this one down here, it is basically horizontally straight across. How far is the distance from P to A, which would be from there to there, you see, straight across. That's purely a horizontal movement on this diagram here, okay, because that's from above. You don't get any height changes when you're looking from above. So that X is that X there. That's very important. To get this X here, we need to look at the right angle triangle. We've got opposite over adjacent. We can do that. We've got opposite over adjacent, which is tan, so we've got tan 50 equals X over 2, so X is 2 times tan 50, and that's about approximately equal to 2.38. Okay, so that's rounding to 2 decimal places, and that's kilometers. 2.38 kilometers. So we can now put that in here, 2.38 kilometers, 2.38 kilometers there, and we've got an opposite and a hypotenuse here. We also got tan on the other triangle, so tan of 20 degrees equals H over so tan 20 is H over 2.38. H then equals 2.38 times tan 20. Make sure in degrees made on your calculator, and I get 0.868 kilometers, or you might want to find it more appropriate to say it's about 868 meters high.